This next lecture is going to be on changing variables in differential equations. So this is actually a useful technique in its own right, but the main reason I'm going to talk about it now at this point is it'll give us a chance to review some really important ideas from calculus. So suppose we have a differential equation that looks like this: dx dt equals some function of x and t. So x is the dependent variable, t is the independent variable. We're solving for x of t. And let's actually say that we have another function. We'll call it y equals g of x. So y is some function of x, which is in turn some function of t. And so we can ask the question, what differential equation does y satisfy? And that's the idea of changing variables in a differential equation. We're changing from the variable x to the variable y. And potentially we can get a differential equation in y that's going to be easier to solve. I'll say immediately what the main tools are. So the main tools are going to be implicit differentiation and a chain rule. Differentiation and a chain rule. Recall what the chain rule says is dy dt, if we're looking for dy dt, that's going to be dy dx times dx dt. And you can probably see how this is going to be useful in our situation here. Okay, so I'd like to look at a couple examples, and we'll sort of learn how to do this in the context of these examples. So example 1 is going to be a mixing problem. This is a typical kind of problem that can be solved with differential equations. So the setup is going to be, we have a water tank. So a tank is going to contain, let's say, 100 liters of pure water. Okay. And then we're going to introduce salt water. So salt water with a salt concentration of, let's say, 5 grams per liter is pumped into the tank. So it's pumped in at a rate of 2 liters per minute. 2 liters per minute. Okay, so we're pumping in salt water, and we're also going to be pumping out water at the same rate. So and a well-mixed solution. Well-mixed solution is pumped out at the same rate. So let's maybe try to draw a picture here. So we have our water tank. Okay, and maybe we have a pipe coming in here. Okay. And then maybe down here, there's going to be a pipe coming out. And we have water coming in here, and we have water leaving here. So this water here is coming in at 2 liters per minute. And let's recall, so this is actually going to be salt water, so it's going to have 5 grams per liter of salt. And the water is going to come out at 2 liters per minute. And the tank is going to contain, as we see here, 100 liters of pure water. Okay, so it's filled with water. All right, so what would we like to understand in this problem? So we want to understand well, natural thing we'd like to understand is how much salt is in the salt water coming out of the tank. So it starts out with 100 liters of pure water, but we have salt water coming in, and then it's mixing around in here, and some of it's coming out. And so the concentration of the salt in the tank is changing over time. The amount of salt is changing over time. Let's say we want to understand exactly, let's call S of t, the amount of salt in the tank at any time, and that's going to be measured in grams. Okay, so I'm introducing this example because I think we should always be trying to get as much practice as we can setting up differential equations from physical problems. And this is a classic physical problem that results in a differential equation to solve. So what is the first question we're going to ask? Well, we're going to ask, what is ds dt? So how is the amount of salt changing? Okay. So let's think about that for a minute. Well, it's changing in 2 ways, right? So there's some salt coming in the tank, in this salt water here. Then there's also some salt leaving the tank in maybe a more complicated way. That actually is going to depend on how much salt is dissolved in the tank at any given time. So a typical setup here is we're going to have some contribution from this incoming pipe and some contribution from this outgoing pipe. And so our expression for ds dt is going to look like this. So we're going to have the rate in of the salt, right? And what are the units here? So ds dt, that's going to have units of grams per minute, right? So grams per time. So it's the rate in of the salt and grams per minute. And then we're going to subtract off the rate out of the salt. So how much salt is leaving the tank through the outgoing pipe? Again, this will be grams per minute. Okay. Okay, well, how much is coming in? That's going to be probably the easier part. So there's 2 liters per minute of water coming in, but each liter is going to have 5 grams of salt. So altogether we have 2 times 5, or 10 grams of salt per minute coming into the tank. How much is leaving the tank? Again, we have 2 liters per minute of water coming out, but we need to figure out how concentrated that water is and how much salt is in that water. So let's actually figure that out really quick. So what is the concentration of salt in the outgoing pipe? Well, there are 100 liters of water in this tank. And so if we knew how much salt was in this tank, then we'd know how much salt was in each liter coming out. It would just be the amount of salt divided by 100. But we don't know how much salt is in the tank. That's actually what we're trying to find, right? That's S of t. But that's actually good for us. So we can actually write down the variable s. So there's S grams of salt in the entire tank, which means that there is S over 100 grams per liter of salt coming out in each liter. So that's the concentration of this salt coming out. And so let's write that down. So yeah, again, so we have this many grams of salt per liter, but we have 2 liters going out, so we're going to do 2 times S over 100. And we have our differential equation. So we have ds dt, and we have actually the variable s appearing over here, the function s appearing over here. Let's simplify this a little bit. So ds dt is 10 minus, what is this, 1/50th times s. And that's our differential equation. Okay, so how is changing variables coming into this, right? We haven't changed any variables yet. So that was just to get practice setting up this differential equation. Let's suppose that instead of the total amount of salt, we just want to understand how concentrated that salt is. So what if we instead want a differential equation for the concentration of salt, so C of T, which is the concentration of salt, and this is going to be units of grams per liter. Okay. And you can try this using a similar method that we just did, kind of just start from scratch and try to write down a differential equation. It's actually a little bit tricky if you try to do that. And in fact, we don't need to do that. So we're actually just going to use this differential equation here. We already did the hard work to drive this differential equation. We can almost immediately write down a differential equation for dc dt instead. And the way you do this is you ask yourself, how are these two quantities related? So how are S and C related? Okay. Right. So the answer, well, S is the total amount of salt. And how do you get the total amount? Well, you just multiply the concentration by the volume, right? So it's going to be 100 times C. S is 100 times C. That's the relationship between S and C. Now what is the relationship between ds dt and dc dt, which is what we want to write down. We want a differential equation that we can solve for C of t. Okay. And this is where we're going to use implicit differentiation. So the idea is you take the derivative of both sides of this equation, but with respect to t, right? Because we want these dt's to appear. So we get ds dt equals 100. And then again, we're taking derivatives with respect to t. We're thinking of both s and c as implicit functions of t, which they are. So we just get 100 times dc dt. We're not taking the derivative with respect to c, but with respect to t on both sides. So this actually gives us the relationship between ds dt, dc dt. And so what we're actually going to do now is just plug both of these in. We're going to plug both of these. So plug both of these equations into the differential equation above. Okay, so this one right here, this one right here. So let's get a new page. And so what is that going to give us? Here's our differential equation. So ds dt is 100 dc dt. And then we already have 10 minus 1/50th times s. But what is s? We want to change the s to c also. So s is 100c. 100c. And now let's just multiply both sides by, I guess, 1 over 100. So we just get dc dt by itself. And we have 1/10 minus 1/50 c. And so this is our differential equation for c of t, or dc dt. So that's how changing variables works. If you want to change from one variable to another, you just ask yourself how they're related, write down that relationship, take derivatives with respect to t, so you're doing implicit differentiation here. And then finally, you're essentially going to plug everything back in to try to eliminate these variables s and replace them all with c. So let's see a slightly more complicated example where we're going to have to use the chain rule. So let's do another example. So this is example 2. And this one is going to be a melting snowball. Melting snowball. Can really model a lot of things with differential equations. Okay, so we have a snowball. It's a spherical snowball. Spherical, because that's redundant. Spherical snowball. So it's going to melt in the sun at a rate proportional. Actually, I should stop here. So yeah, what is this rate going to be proportional to? How fast is this snowball going to melt? What is that going to depend on? I'll give you a second to think about that. Okay, so if you think about it, well, how does it melt? Really, the part that's melting is the part that's exposed to the sun, right? So the surface of the snowball. And the surface is going to melt away. And so, actually, we should expect this snowball to melt at a rate proportional to, what should I write? I should write its surface area, right? So, its surface area. Okay. I think we want to maybe recall a few formulas for his volume of a sphere. Probably need. That's 4/3 pi r cubed, and the surface area is going to be 4 pi r squared. Okay. So again, this is volume, and this is surface area. Surface area. Okay, and what would we like to understand? So we want to understand let's say how fast the volume of the snowball is changing with time. So how fast is it melting, essentially? This is the volume at time t. Okay. And if you think about it, you know, what do we mean by melt? So melts, doesn't that just mean loses volume? So melts is the same as losing volume. Loses volume. So this snowball loses volume at a rate proportional to its surface area. So dV dt, the change in volume, is going to be proportional to k times, and I need a minus sign, right, because I'm losing volume. The derivative should be negative. Proportional to k times the surface area. So surface area is S. Okay, so I could write down S. I guess I'll write down 4 pi r. 4 pi r squared, sorry. And you probably see the issue here. So I have dV dt here. R is going to be a function of V, right? Because as volume changes, R changes and vice versa. So we'd really like to write this R in terms of V instead. So How do we do that? So let's quickly solve for, well, I guess we solve this relationship here, right? V equals 4/3 pi r cubed for the variable r, right? For r. And what do we get? We get r equals, okay, I guess it's gonna be 3v over 4 pi, and I have to take a cube root. So so yeah, this will be to the 1/3 power, so cube root. Okay, so now we can finally write down a differential equation that just involves v. So we have dv dt equals negative k times 4 pi times r squared. Well, here's r right here. So we have 3v over 4 pi to the 1/3, but we're squaring it, so it'll be to the 2/3. Great, so that's our differential equation that we can solve for the volume v of t. Okay, so that's great, but that's a pretty complicated looking equation. This 2/3 power is kind of nasty. I mean, it's not that complicated. We're actually going to learn how to solve this in the next lecture. But I'll show you a really cool trick here. This is really neat, I think. So what if instead, what if we want a differential equation for, instead of volume, how the volume changes in time, what if we instead look for a differential equation for r of t, the radius? R of t, the radius at time t. Okay. So we want dr dt equals some expression just involving r. How do we get that? Well, again, we ask, so this is how you change variables. So we ask how are r and v related? R is the new one. V is the old one that we already have the differential equation for. So how are these related? Well, we can just write that down. It's clear how v and r are related because we've already written it down a couple times actually. Right? V is 4/3 pi r cubed. Okay. And now, remember what we're going to do here. We're going to take the derivative of both sides with respect to t. So we get dv dt. That's this one that we have over here. Equals, okay, so now we're taking the derivative here with respect to t. R is some implicit function of t, right? So we're going to get, by the power rule, we have 4 pi r squared. But then we have to multiply, so be careful here, we have to multiply by dr dt, by the chain rule, right? Because r is an implicit function of t. So we have to multiply by its derivative. If you'd like, you can think of this as you know, this thing we wrote down here, right? So this dv dt is, this right here is actually dv dr. Just the derivative of this, just with respect to r, time, but we need to multiply by dr dt, right, by the chain rule. Okay, so now what we're going to do is we're going to take both of these and we're going to just do some algebra. We're just going to plug those into, I guess we could do either one of these equations here. Okay. dv dt is what? 4 pi r squared times dr dt. And that's going to equal, actually, notice I can just use this one even. I could also write this down and then plug this expression in for v, but then I think we're just going to end up with this again. So this equals negative k times 4 pi r. Oh, something amazing is happening, right? We have the same thing on both sides. We just cancel that out, and we get dr dt equals negative k. Negative k, just like the constant. So dr dt turns out to be a constant, which actually tells us something really cool, right? It tells us that the radius is decreasing at a constant rate as the snowball is melting. This is not true for the volume, right? The volume satisfies this much more complicated looking differential equation. The rate at which the volume changes actually depends on the current volume, but the radius doesn't work that way. So the radius is always sort of going down at a constant rate. And you can try actually, look on YouTube for videos of snowballs melting, I guess time lapse, and you'll see that the radius just goes in at a more or less constant rate. Okay, so I want to give you some practice doing this, changing variables. We'll actually stick with the same snowball problem. So here's a problem for you. Okay, so we considered v of t, and we considered r of t. Let's now consider s of t, so the surface area. How is the surface area changing with time? So I'm going to ask you to find a differential equation that the surface area satisfies. So what differential equation does S of t, the surface area, satisfy? So you're basically going to imitate what we just did. You're going to try to relate surface area to, I guess you could choose either the volume or the radius. Write down that relationship, do the implicit differentiation, and then do some algebra to come up with a new differential equation. And that new differential equation should look like ds dt equals some expression just involving s, and possibly various constants. Okay. So I guess that'll be it for this lecture. Actually, I want to say one more thing. So just because we can actually solve this differential equation already. Because this one right here, certainly, we know how to solve this. All right, so if dr dt is negative k, then r of t is simply going to be negative k times t plus arbitrary constant. C can be any constant. And then we have the function r of t, we can just get the function v of t. How do we get the function v of t? Well, the volume is always going to have this relationship here with the radius, right? It's going to be 4/3 times pi times the cube of the radius. So let's just write down what the solution of this differential equation is going to look like. V of t is going to be 4/3 times pi times the radius cubed, but we just figured out what the radius is doing with time. It's negative kt plus c, and we're going to cube that. And again, c can be any arbitrary constant. And we actually just solved this differential equation by using this separation of variables trick. We found or not separation of variables, sorry, that's what we'll talk about in the next lecture, by doing this changing variables trick, right? So we found a good change of variables. Replacing v with r, that actually made the differential equation much simpler. Those changes of variables are hard to find usually, but sometimes it's pretty clear what they are. Sometimes it's not so clear. In any case, next lecture we're going to talk about how to solve a differential equation like this and many more kinds of differential equations. So I will see you next time.